This week, we begin using physics in earnest to motivate our views of sound. We begin with the simplest physical systems that do interesting things for us. The simple pendulum, consisting of a string and mass, and a simple mass spring damper system. Both oscillate smoothly with a regular and predictable frequency. We'll look at these and use them to motivate our first physics-based sound models. First, we'll investigate the mass spring damper system, which is characterized by a spring which exerts a force on a mass which is linearly proportional to its displacement from rest position. So if it's at rest, there's no force making it move. If we displace it from rest and let it go, then it oscillates, as we'll find out soon, in a sine wave pattern. The important physical constants determining this are the spring constant, which is how much force per unit displacement, and the mass of the ball inside here. To show this, I'm actually going to add another ball into the system to give us more mass. So we've doubled the mass by adding the second ball. First thing that we'll notice is that the rest position is lower because it's pulling harder against the spring constant. The second thing we'll notice is that when I let it go, it oscillates slower. This is the equation governing the mass spring damper system, which says that the acceleration on the mass is a function of the spring constant and the displacement. There is an additional force due to the damping, which acts proportional to the velocity of the mass if it's moving. We can solve this in the computer by approximating the velocity as the first difference of position. In other words, the position now minus the position a little bit of time ago. And by approximating the acceleration as the second difference in position, or the first difference in velocity. So velocity, for example, we're familiar with as miles per hour or feet per second. Acceleration would actually be then given as feet per second per second. We can use this in the computer to solve this system by adding accelerations to form velocities. Acceleration comes from the forces on these balls. We can then use the velocities to form positions. That's what this code does. Here's a little mass spring damper. We can displace it from rest position, and we can let it run. It's doing the exact same thing as our system here is, except faster. But we can change that. We can double the mass, and it will run much slower, just like it did when I added the extra ball. Here, unlike in this system where we'd have to replace the spring, we can change the spring constant because it's just a number inside this computer simulation. So now we have a higher spring constant and the system runs faster. We can reduce the damping to 0 and the system will run without decaying at all. It essentially oscillates forever because there's no loss due to friction or wind velocity or anything else that's acting on this real-world physical system. Now let's look at the pendulum system. Here, the restoring force is a function only of the angular displacement and gravity, which acts as the spring in this case. Interestingly, the mass doesn't really play a role here. Some mass has to be present, but the forces aren't dependent on the value of it. The equation governing this system states simply that the angular acceleration, which pushes it back towards rest, is a function of gravity and the length of the pendulum string. So if I let it go, it oscillates, as we'll see soon, in a sinusoidal motion, in a sine wave. If we were to shorten the length of the pendulum, it would swing faster. Again, that dependency on length. We can't change the other force in this, the spring, which is gravity, but we can in the computer. So let's look at the simulation. Here we now have a pendulum stuck at rest position, just like when I was holding it off to the side. If I let the system run, it oscillates with a sine motion. The curve is showing its displacement from equilibrium as a function of time, and it swings gradually back and forth smoothly Its fastest velocity is through rest position, and then it slows to zero velocity at maximum excursion, and then back and repeats. This system doesn't have any damping in it yet, so it will swing forever, unlike the real-world physical system. I can introduce damping by simply changing a number, and we'll see our pendulum die away. I'm going to take damping back out, put it back to its displaced position, and play around with the other two physical constants in here. One, gravity. I'm going to increase gravity. Look at that. It goes a lot faster. So on a larger planet with more gravity, pendulums would swing faster. On the moon, it might swing very slowly because there's less restoring force. The final physical constant in here doesn't matter, the mass. I can play with the mass all I want and nothing happens whatsoever. It's not intuitive, but you should try an experiment of your own with a string, a golf ball, a tennis ball, a baseball, different balls of different masses, and you'll note that the pendulum swings at exactly the same speed. So now we have seen multiple real-world systems, all of which oscillate in a sine wave pattern. Another name for the motion of the pendulum and mass spring is simple harmonic motion. Because they're so fundamental to physical systems, and as we'll see soon, they're important to our perceptual systems as well, we're going to see lots more sine waves for the rest of this course.